I deliberately didn't post the average, which was 90.7, which is very high, because I didn't want people to feel bad if they had an 89 or an 88 and think they're below average. That's still a great score. And I wanted to explain partially why the scores are so high. And it's because we grade with continued error, meaning we give you tons of partial credit. So first of all, did everybody pick up their exam? If you didn't, you should come and get yours right away so you can make sure it was graded correctly. They're down front if anybody needs to get one. All right, so look on the front, and these are the points that you missed. So if you have all zeros here, you got 100%. That's great. So those are the points you missed, and make sure it was totaled correctly. So go down and pick up your exams if you haven't already done so. Now, basically on this page, there was no partial credit. I just want to make sure that yours was graded correctly. If it wasn't graded correctly, then see me after class. I'll let you out 5 minutes early so that you can see me after class. So just check these numbers. And people did really well. I'm not going to, on this part, most everybody got this. And again, this key is on Compass. And here some people got these wrong, so maybe it would help to just go over it a little bit. All right, so it says, which of the following will increase the power of the test? Increasing the probability of a type 1 error. So if we look this way, increasing type 1 would be moving it like this, and clearly that would make the power bigger. Increasing D, the effect size. Well, the D, the effect size, is the difference between the null, right there, and the alternative, the hypothesized null and alternative. And clearly, if we made this a bigger difference, this whole graph would move out and the power would increase. A bigger difference is easier to detect. So you have more power in detecting it. Increasing the sample size. Increasing the sample size, what does that do? That makes it would serve the same effect doing this. Another way to visualize it is that when you have a bigger sample size, you have less sampling error, more precision. So basically, this curve, the error around both of them is going to decrease. So the area is the same. If the error decreased, you'd have the same area. Imagine if we just really drastically did it. See how just about you could make it those small enough errors that they're completely separated, the two curves. Does that make sense? Okay, and increasing the standard deviation, that increases the standard error. If there's more variation, you're going to have more standard deviations, going to be bigger error bars, right? And so it's going to be the opposite. It would spread out, and it would decrease your power. And it's easy to remember because the power, the less error you have, the more power your test has to detect a difference that's really there, the more precision it has. Does that make sense to everybody? All right, so let's move on. Now on this page, there was something called continued error. What does that mean? You can see that your answers depend on what, for example, your answers below depend on what you calculate here. So if you get this wrong, or you get this wrong, then, or this wrong, etc., you're going to, it's going to follow you throughout the exam. So basically, we grade you. If you see CE, something called continued error on your exam, that means that you made a mistake at the beginning, but your logic was correct after that. So you got the wrong answers, but we still give you credit. The point is that we don't want to deduct more from the same type of mistake just because, depending on where it occurred in the problem. If you don't grade this way, then an error, if you make a careless error or even a conceptual error at the beginning of the question, is going to cost you everything. Whereas opposed to the same type of error at the end will only be deducted a little bit. And I didn't think that was fair. I used to hate it when I was graded that way. So throughout, if there's any type of continued problem, like there is, on the 5th page, there's a lot of it, we grade you that way. And that's part of the reason why the scores are inflated. For example, I went through a number of times, not this semester, but past semesters, where I graded people the way you're often graded. It's much easier to grade that way, just right or wrong on every part. And generally speaking, people scored about 10 points, on the average, scored 10 points less. So instead of having an average of 90.7, I'd probably have an average in the low 80s, about 80. And so part of the reason my averages are very high on the exams are because I really pay attention to the type of mistakes you make and don't just say, blank, hey, it's wrong, I'm marking you wrong. That's the whole point of why we grade, we hand grade. Because we don't want to, certain types of errors aren't as bad as other types of errors, and we want to differentiate more. So that's part of the reason the exam scores are so high. Warning, final exam is all Scantron and the averages are lower, just because of this. Possibility of not being able to give you continued error. Understand? Okay. So let's just look through and make sure you've got all these. Most people did pretty well here. This was a very hard one to map through with the continued errors. Because people, if they made errors, they got really illogical. It was very difficult to grade, but we tried to do a good job of it. So if your paper's all marked up, but just very few points missing, that's why. This one, I was surprised that people made mistakes because you were given the formula. And the most common mistake was 95% power. Remember, that's 95% all the way to the right and just 5% error. So people mistook it for 95% confidence interval and put 2 here, or 1.96. No, these should be the same. We look 5% type 1 and 5% type 2 error is what it means. And so that was the biggest mistake. And this, some people got this messed up. But the answer should have been 39. Questions on that? 38 we accepted. All right, let's move on. Next one was all multiple choice, so there was no continued error on this page, and people did really well here. I was pleased. And people did really well on this one, and I was really happy about that. In fact, on the design of experiments, questions that people did phenomenally well. And I know some of you aren't native speakers, so that was even more impressive to me. And this was one of my favorite studies. It's a real study to test the beer goggles effect. We all know what that is, right? The beer goggles effect. It happens when you wake up the next morning next to somebody and say, what happened? What was I thinking? That's the beer goggles effect, right? You go to a bar, and this happens to me used to happen to me all the time, like you go, yeah, I'm 64 years old, I hope it doesn't still happen to me, but you'd go to someplace, and you go to a bar, and everybody is so friendly, so nice. They all seem really intelligent if you're drunk, right? But if you're sober and you go to that you'll get so bored. I highly recommend not getting into conversations with drunk people when you're sober. So it's the same effect. You think everybody's attractive and it's your friend, and so you end up rating them very attractive. And this is a beautiful experiment that shows that effect. A randomized experiment. And I love this. I thought it was a great experiment. And it was a very clear beer goggles effect. So, because the groups were balanced to begin with, there were no confounders. Understand? All right. The next one was you did phenomenal on, and I was really happy. This was a question that was pretty difficult. It was an observational study that saw that there was a positive correlation between how much antibiotics were prescribed over a 17-year period to women and how many breast cancer diagnoses they got. And they got twice as many if they had women who filed 25 or more prescriptions for antibiotics over a 17-year period received breast cancer diagnosis at twice the rate. So this was all over the news a few years back, and of course people were investigating a causal link. And one possible cause could have been that those antibiotics kill not only bad bacteria, but healthy bacteria, and healthy bacteria that could prevent cancers or breast cancer. So that's one possibility. They didn't investigate, at least in the studies I saw, certainly not in the popular press, they really didn't think about any confounders. So I thought of two obvious ones, and everybody picked, not everybody, but the vast majority of people got them both, and I was shocked. That's really good. The underlying immune problem, that those who have some kind of immune problem, if you have a weak immune system, it's certainly going to lead to more antibiotic use. And also, a weak immune system can lead to a higher cancer risk. If your immune system is weakened, you're more likely to get cancer. So that's the confounder. And this one's in previous exams that I've given this question, almost people really missed this one. And you guys got it, so it was pretty amazing. So it says women who regularly go to the doctor, right, are both more likely to be prescribed antibiotics, and they're also more likely to get mammograms and breast exams, and more likely to get a diagnosis of breast cancer. All right, so that's the confounder. So I was super happy about you doing so well in this, and you understood very well how to break into subgroups, block, how to stratify. Okay? If we thought income was also a confounder. Let's move on. All right, so here on this page, there were lots of continued errors. People got a lot of mistakes, so you'll have to look at your own paper. One thing, most people got this. Let me see. Here's another. I was writing continued error everywhere. Okay, so this was rounded. If you didn't round it, you get 3, 3, 3. You know, and so that was. So if you have a confidence interval, it looks like that, because you're adding and subtracting 0.1. All right. Now, when you computed this z statistic here, if you used this rounded answer, you would get 8. But if you computed it with the non-rounded answer, you get 7.5. Or if you did it this way, you'll get 7.5, because that's like the non-rounded. So either one we accepted. And down here, I didn't mean this to be a tricky question. I said if you converted all the heights from inches to centimeters, then clearly the z-score and the p-value aren't going to change. They're not unit dependent, but the slope is. So why does it not change? I didn't mean to. In fact, I thought when I first wrote this question, I actually got the wrong answer and thought it would change and multiplied whatever you got here by 2.54 centimeters per inch. But then I realized, well, yeah, it's not going to change. It does not change. Why? Does not, the confidence interval for the slopes does not change. Why? Because the slope is SDY, depends on SDY over SDX, right? And that's not going to change. Each one of those will change by 2.54, but then the ratio doesn't change. All right, so what did we do? This was worth 2 points. I thought this mistake wasn't so bad, multiplying by, so I only took off 1 point. If whatever you had here, you multiply by 2.54, I only took off 1 point. If you made a worse mistake, I took off both. And this, of course, I didn't take off any points. Questions on any of that? All right. Now, let's see this last one. Okay, so here, some people messed up this formula, and then, of course, and everything got messed up, but we tried to give you continued error here. Let's see, and we gave you continued error if the relationship between, even if we got this one wrong, if the only difference was, that relationship, then we should have given you continued error there. Okay, there's a lot of people are a little bit confused about this difference between a one-sided test and a two-sided test. Since we're going to be looking at that more, and especially today, let's make sure everybody understands this. So here, if we're testing, if the alternative is one-sided, the null is the slope in the population 0, and our alternative is we think that it's greater than 0. So we think it's directional, it's out here. So when we get this p-value, we get this slope that translates into a 2.25 z-score. We say, okay, what's the probability of getting this extreme a slope or even more extreme in this direction? Only because this is the direction we know something, we think it's going to be greater than, so we're not thinking about that direction at all, so it's the area of that tail. Now, suppose you knew less. You just knew that, okay, I don't think the slope's going to be 0. I mean, I think it's going to be different than 0, but I don't know if it's going to be way out here or way out here. Like if I didn't know what, imagine with a coin that you thought was fake. You thought the coin was fake. You thought the guy was a trickster. He was going to, he had a fake coin. But you don't know if he made it fake by giving it too many heads or too many tails. You don't know. So then you would test a two-tail. You'd say, okay, if I get it out, but since you're not sure in either direction, if you get, you have to count both tails. You don't know as much to begin with. You don't know, hey, I know he has a coin that he always weights towards heads. Then if you knew that, your alternative is going to go this way, and your p-value is the area of this tail. But if you know, you might as well use your knowledge ahead of time, right? But if you don't know anything, well then you're saying, what's the probability that I get this extreme value in this direction or in that direction? It happened to come out in this direction, but you have to count that tail too, so it's twice. Basically, you need stronger evidence to reject the null when you don't know as much to begin with. If you use what you know ahead of time and you think it's going to be one directional, then you should just use a one-tail. Now, granted, in programs, most software just does the two-tail, but it's up to you to decide whether you want to cut that in half or not, depending on what your initial hypothesis is. You got it? All right. So that's pretty much it. And now we're on chapter 11, and we're going to start exam 2 material. And you're going to have your exam 2. When is your exam 2? I think it's the Thursday before spring break. That day is your exam 2. So this is the start of exam 2 material. Okay. And today is Tuesday, 2/16/16. All right. So we're still on simple linear regression. 1x quantitative variable predicting 1y quantitative variable. Okay? Like exams predicting final, drinks predicting GPA, etc. All right. Now, but we're going to look at a more general way to do regression estimates, or a general way to do predictive models, not only regression, but we're going to be comparing several means this way, etc., using something called analysis of variance. All right? So analysis of variance provides this basic framework. It can be used for all predictive models. All right, when you're predicting y from some function of x. Okay, that's what I mean by that. As long as certain assumptions are met, which we'll talk about in a minute. It checks whether adding parameters to a model, by making it more complicated, adding some parameters to it, improves the accuracy of your predictions significantly more than would be expected by random chance under the simpler null-dull model. So you get a test statistic called the F ratio to compute p-values. And for simple regression, this F stat is just going to be the square of our t statistic. So for simple regressions, this analysis of variance is just another way to get the same exact p-values we did in chapter 10 for the slope that we get from z and t-tests. If you square this, for simple regression, you have 1x, you square the t, you'll get the f-stat, and if you square the z, you'll get something called a chi-square statistic. But I just thought it would be a good idea to show how it works in a very simple case, so you can understand how it can work in more complicated models too. When we go into multiple regression and we add multiple x predictors, independent predictors, for our dependent y variable. All right, so I thought it's a good time now, after our first exam's under our belt, to start moving into a little bit more formal notation. So if you want, and we're doing these hypothesis testing, and we have this population regression equation for the simple linear model where you have y is equal to, this is your intercept, beta naught, this is your slope, right here, and we just have one slope because we have 1x, right? And this right here is your errors. And the assumption is when you're doing these hypotheses tests, significance tests, is that these errors right here are normally distributed. They look like this. Your errors around your regression line are normally distributed with mean 0 and the same variance. The same variance no matter what, like within each vertical strip. That same, like the same spread, that you don't have bigger error bars when you're predicting y from bigger x's, let's say. It's the same throughout. And so these are your errors. And another way that you'll probably see this is people say IID. Of course, they're independent, identically distributed errors, 0, sigma squared. They usually talk about the variance. So this right here is what we estimate. This is estimated by our standard deviation of the errors. Now look at this. You notice these Greek letters, all of a sudden I've moved into Greek letters here? That's because the way that in general the rule is that you use Greek letters for the population parameters. That's some ideal think of Greek letters as Greeks, ideal, the beautiful model that you have out there, right? And so you use these Greek letters for the population that you're trying, and then your sample's all messy. You get a different sample, you have errors in it, and you use Roman letters like B, and S here for estimating our, and E for errors instead of epsilon, for estimating our beautiful population parameters, or our model out there that we don't know. So that's sort of the rule of thumb. Either that or you put hats for our predictions, little hats on top of these. Okay, so now, all right, more notation. So y is an observed value of capital Y, which of course is all, if it was, if we had 100, we had 200 or 198 final scores, exam 1 scores, if I was trying to predict those from your homework. So this y vector, you could think of it as a vector, is going to have 108 numbers in it, and here's a particular observed value, okay? And then here's a particular predicted value. And y bar is the average, or the mean of all the y's. So now what analysis of variance does is it breaks down the total variation around, for example, your exam scores. The average was 90.7, but of course there was variation. Some people did above average, some people did below average, by quite a lot. The low score was, I think, 20 maybe? Something like that. So some people went really low. Of course, you couldn't get above 100. So, so we want to, let's say you wanted to predict that variation in the y's, the variability in the y's, and you can break it into, I mean, if everybody got the same, if there's no variation in the y's, that means everybody would have gotten the same exact score, and there'd be nothing to predict, right? So let's say I wanted to predict your exam score from your homework, and so I would, with a linear model, and what we're doing here is we're breaking down the total variability of those exam scores into two parts. One predicted by the model, one predicted or explained by your exam scores, and the other just left in the error. We're breaking that variability into two parts. So this is called the sum of the squares total. You can see right here. This is where we're going to. Let me just, so this is the total variability, the sum of squares for the y's, and we're going to break it into two pieces. One will be the variability explained by our model. In this case, it would just be by our slope, really. And this, we call this is like our signal. And then what's left in the errors. Okay. So this right here is the noise. So we're trying to separate, we're trying to model these y's, and we're going to have, and the variability will be broken into two parts, our model and our noise. Okay, so let's look at this. So the sum from I equals 1 to however many observations we have of your y minus your average squared is the sum of squares total, right? So for example, if the average, let's say, was 90 and you got a 95, then you would have your, that you'd be 5. You deviate by the average by 5. If it was, if you had 80 and the average was 90, your particular score would deviate from the average by -10. And if we summed them all up without squaring, you would get 0. So you square them to get rid of the sign. You square all your deviations, and then you add up the sum of the squares, and that's what this is. Now, if you took its average divided by however many scores there were, 198, that would be called the variance of y, and then if you take the square root of it, that's called the standard deviation of y, right? So this is like the first step on the way to computing a standard deviation. It's called the sum of the squares. And that's what we're looking at when we look at, do analysis of variance. Now here you have the sum of the squared errors. So what's this? This is your particular, let's say you got, a 95, and from our regression equation you were predicted to get a 92. Well then it's your observed minus your expected, that's your error. And again, if you sum up all the errors, they sum to 0, so we're squaring them all. We're doing the same thing here. These are, and then that's the sum of the squares, if we do that. If we take its mean, it's called the variance of our errors. And if we take this, take the square root of the variance, it's our old friend, the standard deviation of the errors, which we know is the square root of 1 minus r squared times the standard deviation of the y's. Now some people have asked, a few people wanted me to prove this mathematically, so I figured rather than do it in class, I put it, and some other things too, people have asked me, because you're going on to higher classes and you're interested, a lot of people in here are math majors, so I'm putting it in a folder called Appendix on your compass. So right now this is explained as proved if you on compass. If you want a more rigorous mathematical proof, I can provide you with one, but I tried to do semi-halfway, intuitive halfway. You can see what I put up there to explain this. And if you want anything explained, I know some of you really need to be convinced by mathematical proofs, please, I'd be happy to provide that. It's just that most of the people probably don't want to see that worked out in class. If you do you? Raise your hand if you'd like me to work out mathematical proofs in class. Raise your hand if you'd prefer them just in the appendix. Okay, yeah, overwhelming. So, but if anybody wants, after you read the appendix, you don't understand it, just come to me during office hours and I'd be happy to explain it to you. All right, so you can see that one now on the appendix. Now let's see what else we're doing. Okay, so now Okay, so we've got this null and alternative hypotheses, and the null is just that this was just our population slope is equal to 0, that's what that is. And the alternative hypothesis, look, for all of these, we're going to be looking at sums of squares. So it's always going to be non-directional. We're always going to have basically a two-tailed alternative if we use the F or the chi-squared statistics. Okay, so that's the basic idea. The intuition behind it is like if you have an individual observation Y, then, okay, so this is how far from the average it is. Because remember, we're trying to see if we're doing any better than just estimating the average for everybody, okay? So this is how far from the average a particular observation is. And this right here, this part, is how far our predicted is from the average, how much our prediction improved upon the average, and this is what our error is. So this is like the model, how much an improvement our model made, and this is how far off we are from our model. And you can see it's a tautology here. I mean, this has to be, y minus y bar equals y minus y bar, right? That's all that says. So the question is, so now what this is just, okay, so can we go from this, which is just the tautology, right? I mean, that's just breaking, it has to be true. Can we go to, like this says, C equals A plus B? Well, we can't go, what I did here was say, okay, C squared equals A squared plus B squared. And that's only going to be true if you have basically a right triangle, right? The Pythagorean theorem. So in other words, it's only true when our errors are basically at right angles to our prediction line. And that is the shortest distance. That's how you minimize the sums of squares. And that's the proof that I also have up in the appendix. It's basically the same proof, same idea. So it's because of the way we do our least squares estimates to minimize our errors by dropping a vector that's orthogonal, that's at right angles, so this, to make this true. So that's why we can do that. Anyways, you can look at that if you want a more see appendix online. This is on Compass. Meanwhile, here's how you can understand it very simply and visually. I mean, here's the picture, just in 2D here. And what we're doing here is we're just saying, first of all, this is our, this regression equation. This is what we got right here in chapter 9, right? This is our same example. This was our simple regression equation, so I'm just using the same data here. And so for example, let's look at this guy right here, student D right here. He actually got an exam score down here of 92, right down here, and he got a final score of 95. Okay, so this is exams predicting final, right? So that's what he did. And so let's look here. So this right here is his y value. 95 is his y, right? Okay, so that's, I'm just showing y minus, it's just very, very simple. Whoa, what do I have here? Sorry, that's just, there shouldn't be a bar there. That's just your y hat. I'm really sorry. Okay. Now, so this is y, right? And then his, so we're saying this distance we predict the average of everybody was 74. And right here, this right here is 74, and that's y bar. Okay, so if we just predicted the average for everybody, we'd be off by 95 minus 74. This is 21 right here. 95, that's 21. And all we're doing is we're saying, okay, for each one of these, we're breaking into two parts. Our prediction, right here, this is our regression line. So this is our model. This predicts what? This is predicted, got 74, but our model predicted 79. So that's y hat. So it was an improvement of 5. It's right here. That's due to the model. We got an improvement of 5. But we still have this little piece. We still have this piece. 95 minus 79, that's the 16 to the error. So we just broke it into two parts. Well, here for E, it's all model and no error. We made a perfect prediction for E. For like this person C, we would have done better using the average. We got further away with our regression line. So that's basically the idea is for each one of these, you sum the squares of the errors. Okay. Does everybody, understand? Should I move on? Questions? Okay. So, now, so one thing that I talked about before was this R squared. And you've probably heard, and we talked about it before, is the proportion of the variability of the y's that's explained or predicted by the model. And 1 minus R squared being the part that's left in the errors, right? So the way that you can think about it now in terms of partitioning the variability of the y's up, we can think, okay, so we have this R squared plus, we talked about this before, like on page 34, right? You know, R is just your correlation coefficient squared. It's positive all the time. Actually, capital R is the absolute value of little r for simple regression. So this was back on page 34. All right, so now we're really going to dive into this and look at it more. And so we have R squared, which is our correlation coefficient squared. And that obviously is going to be the strength measure of the strength of our model. If we had perfect predictions, this would be 1. And 1 minus R squared would be 0. We'd have no error. And this, I'm just saying it equals to 1, right? R squared ranges between 0 and 1. So this is the strength of our errors. So another way to think of when you do this partition of the variability of the y's, we're trying to break the total variability of the y's, so we'll multiply both sides by sum of squares total. So if you multiply the right, the sum of squares total, and you multiply this by the sum of squares total, r squared times sum of squares total, plus 1 minus r squared times sum of squares total. This might help give you an intuitive picture of what's going on, because this right here is the proportion of the total variability, r squared times SST, is the proportion of the total that's due to our model, explained by our model. And this is the total proportion of the total variability, the fraction of it explained. See what I'm saying? It's the same thing as that. And this is the fraction explained by our errors. And together, obviously, they equal the total. So it's very useful because R squared is given to you in all regression analysis. So basically, these statistics that you get are just the ratio of R squared over 1 minus R squared times some factor that's dependent on your sample size and how many parameters you have in your model. But that's the crux of all your R statistics, are R squared over 1 minus R squared. And you can probably see that was true of our z statistic too, because for the slope, because if you look at our let's look at our exam. Where was our exam? Right here. If you square the z, you get, whoops, you get r squared over 1 minus r squared. And then you're just multiplying it by the sample size here, or for t, you're multiplying it by adjusted sample size. So we'll look at this. So let's do an example, and I think it'll be easier to put this together. Ooh. So all we're doing here is nothing new. I'm just introducing this analysis of variance early. So you're probably saying, like, this problem we can already do, right? We can already do as a t or a z test. You did it on the exam, right? So you could say, for example, we could do it right now if we wanted. We could say, first of all, what are we trying to do? We already did this problem. We're trying to predict whether we can predict somebody's GPA from how much they drink. And we did this, we want to see, last time we took a random sample of 25 students and we got this negative correlation here, but we want to see if that holds up in the whole population. That's equivalent to saying whether our slope is 0 or negative in the whole population. So now I said, and we saw that we got a p-value of like 18, 17, it wasn't significant. Well, what if we do 64? What if we take a bigger sample size? Then is it significant? Okay. So if we wanted to just proceed the way we did before, what would we do? Like the way we just take exactly, you could just do it exactly like you did on the exam, and you could test whether the population slope, the null is whether the slope is equal to 0, and the alternative here for these is going to be non-directional. Here, okay? So we can do that, and we could just say, okay, t is equal to the square root of, we could just use that statistic right here, and we'd say the square root of 62 n minus 2 times what? R, which is negative 0.2 divided by the square root of 1 minus negative 0.2 squared, and we'd get a statistic right there, and we could look at the p-value, etc. But I just want to show you another way of doing it by, why am I even showing you the other way? Because this is only going to work when you have one x. When we have multiple x's, this was like the correlation coefficient minus 0 basically. And when you have multiple x's, how can you even think about a correlation coefficient? We'll have to talk about that later. And you have multiple slopes and so forth. We're going to have to do something different. We're going to have to move into looking at the whole collection of slopes if we're testing the null. That all the slopes are 0. But for now, let's just look at this. Okay, so now, so we could do this, and what would we get? Let's see, do you want to do it? We get the square root of 62. Did I do it? I didn't do it before. Here, I can do it right now. So I get approximately 1.606. All right, now let's do it a different way. Let's try it by this analysis of variance. And so we're going to set up, we're going to say, this is our model. We just have, we're saying that GPA, this is predicted GPA, we have that little hat on it, meaning predicted GPA, is equal to some estimated slope, intercept, plus some estimated slope, right, times the drinks. Now, have what's called, we have two parameters in this model. We're estimating intercept and we're estimating a slope. So it's two parameters. There's two terms on the right-hand side. So our P, our number of parameters, is equal to 2. Okay, so now let's look at this again. So this is our sum of squares total, right down here. And here we said that r squared, and this reflects 1 minus r squared, these two have to add up to 1. And r squared times SST is the sum of squares model, and r squared, that has to add up to SST. This plus that totals that. So how are we going to get any of these? What were we given? Well, here you're given what? How are we going to get this? You don't know, we're not going to do it from scratch. That's too much work. So I gave you the standard deviation of the y's here. So the standard deviation of the y's is right here. We're going to use that. We're predicting GPA, so we're going to use that standard deviation of the y's. And we know the relationship between the standard deviation of the y's and this is the first step on getting the standard deviation of the y's. So the SST is just going to be what? It's going to be, well, it's the variance multiplied by n, right? That's the variance multiplied by n. So it's going to be n times the standard deviation of the y's squared. Right? That's just your sum of squares total. You take the mean of it, and you get the variance, and then you take the square root. So that's the same relationship we just talked about. And so that's equal to 64 times 0.5 squared, which is a quarter of 64, so that's 16. So that goes right here. That's 16. All right, in this case. So now from that, we said that from that we can say, okay, let's get what r squared and 1 minus. R squared times 16 is going to be our sum of squares model. And what is r squared? Well, r squared is going to be equal to negative 0.2 squared, which is 0.04. R is positive. And 1 minus r squared is then 0.96. So we'll just take r squared times, so this is going to be equal to 0.04 times 16, and this has to equal to 0.96 times 16. And together, obviously, they have to add up to 16. So this right here is 0.64. So this obviously has to be what? 16 minus that, so it's 15.36. All right, so just like these add up to these two sum, so do the degrees of freedom. Now the degrees of freedom total, that's like when you're estimating the total variation around the mean, you just subtract off the mean, so it's n minus 1, because n minus 1 observations would deter, if you knew the total, they have to sum to 0, right, the deviations. So all we need is n minus 1 of them to, the last one would be determined. So n minus 1 are free to vary. So this degrees of freedom here are n minus 1. All right, so in this, oh, it's right here. I didn't even have to do it, right? N minus 1. All right, so yeah. So n minus 1, which in this case then is 64 minus 1, which is 63. Now, let's look at these two. So this is, okay, our number of parameters here. So this is p minus 1. That's the same as the number of x's in your model. The number of parameters, basically, this intercept doesn't really matter. So you can subtract that off, and it's p minus 1 degrees of freedom. So here it's just going to be 1 degree of freedom. If we had another x, it would be 2 degrees of freedom. It's the number of x's, same as the number of x's in your model. And this is the same. This is n minus p, which was the same number of degrees of freedom that we had for the t-test. we had a model like this with 2 parameters, so it was n minus 2 was the number of degrees of freedom. We said 2 points determine a line, so we need a third point to estimate the variation, to estimate the errors. So you can see that they add up to n minus 1. So in this case, we have what? We have 2 parameters in our model. So the degrees of freedom here is 1. And here we have 64 minus 2. This has to be 62 to add up to 63 anyway. So that's... You're going to be seeing these charts like this on so many printouts. This is sort of... On software printouts, you get this, you get all these statistics here. So I'm just trying to show you basically how to read them. All right, so then to read these mean squares, what these are is your mean square is your sum of squares divided by the number of parameters. Divided by the degrees of freedom. Okay? So these are the degrees of freedom for your model, this is the degrees of freedom for your error, and this is the degrees of freedom total. So here you just say what? You'd say 0.64 divided by 1. And here you have 15.36 divided by 62. Right. And that is 0.25. Okay. So now, what is this F ratio? This is just the ratio of these two. So it's 0.64. Or you could do it that way. 0.64 over 0.25, which is 2.58. So you could check it by just what we said. The F statistic was, well, if you're given r squared, it's much easier to check that by saying F equals what? Well, it's r squared over 1 minus r squared. And then you have to multiply it by not n, but n minus 2. Okay? So what do you get when you do that? That's 0.04 over 0.96 multiplied by 62. And you should get the same thing, 2.58. So you can check that way. And if you take the square root of this, you'll get 1.606. So, I know I just sort of, I find this pretty tedious. I remember when I was taking stats classes back in the day, we had to compute the standard deviation of the y's from scratch and just go through so many calculations, and by the time I was done, I forgot what I was doing. We will do it for small sample sizes. When we have small sample sizes, I'll have you go through all the calculations, but basically, I don't know, it's simple, especially if r squared is given to you, which is about always is, it's much easier just to think of it this way. Okay, so cut 2 on that. All right, so now to get the p-values and to use, let's go to our next page. All right. So now, we did this already, right? We just did this. We found that, and we found it to be what? 2.58? Okay. And this is how we found SST. We went through all that. Okay. Now, so this F ratio, so this is, all right, so you remember how the T curves were a whole family of curves depending on your sample size? So now, it's not only dependent on the sample size, n minus 2, that was the same for the T curves to test the null that the slope was equal to 0. It's not only dependent on that, but it's also dependent on how many degrees of freedom are in the numerator, so how many parameters you have. And with this case, it's only 1x, but if we had 2x, you'd have to look at a whole other set F curves. So it's depending on two sets of degrees of freedom, the numerator and the denominator. Okay? So, so how did we get the p-value of 0.112? And it's exactly twice the p-value given by the one-tailed test. So this is distributed, that's what that means, as an F with 1 degree of freedom in the numerator and 62 degrees of freedom in the denominator. And we're going to get this. And our t statistic, our t-stat that we got on the previous page was what? The square root of that. You can just check. It is the square root of 2.58. Yeah, and it's 1.606. And this is distributed as a t with 62 degrees of freedom. So what I'm saying is that degrees of freedom, these always match. These are always equal. And this one is just 1 degree of freedom. And if it's more than 1 degree of freedom, we can't use a t-test anymore. A t-test is only applicable if you have one slope or one, the difference between two means. If you're assessing the difference between 3 means, we're going to have to do the f-test because we're going to have to look at the whole collection of differences and not just one single sign number. And this was even negative. All right, should have been negative. I forgot to put that in. We have a negative. You see, this f is always going to be positive because it's squared. This is always going to be positive. All right, so now I want to get this p-value. Where did this come from? Let's look. That p-value. So how do we do this? One thing we could do is you're supposed to look at these tables, the f table. So, but these tables are very approximate because you're going to have a different table for. Here, let me show you. Here's a table right here. You can try it on here. So this is how you would look at how to read the F table, and I try to go through it here. So for the numerator degrees of freedom, all right, so that's 1. So it's going to be in this column. Now our denominator degrees of freedom would be right, this is the closest one, 60. You see, but we have 62, so there's nothing exact here, but it's about right here. So what is this? This is 4 point, so this is what we have here. So what does that mean? Well, that's the cutoff. That's the null cutoff. Basically, a null cutoff for what? For alpha equals, for the 5%. So we'd have to get a statistics bigger than that. We'd have to go further out on the tail to get further out on the tail. So we don't have significance because we only got 2.58. But what about if we had our alternative was directional, that we thought there was a negative correlation? You're not going to think that the more you drink, the higher your GPA, are you? So we actually don't need this. We actually should be looking on alpha equals 10% or a different. But let's just go to our, the easiest way to. These tables are going to be very cumbersome, as you can see. So what everybody obviously does is use the computer. So let's look it up on the computer. What the exact p, that just gives you a cutoff that you have to be above. We want the exact p-value. So what is it? We know it's bigger than 5%. Let's see what it is. Oh, here it is, 11.2%, but let's look it up. So let's go to online. And let's go to our syllabus and go to our course website. And we have a p-value calculator up there for the F distribution. Okay, so remember,
degrees of freedom in the numerator was what? 1, and the denominator was n minus 2, 62. 1x, so we have 1 there. Now our p-value was 2.58. Not our p-value, our f-value was 2.58, and we want to compute the p, and there's 11.33. What did I say? 11.2. Well, this is more accurate. All right. So that is, we have to reject the null and conclude that we can't say that the slope is different from 0 in our whole population. In other words, we can't say that there's a negative correlation among all 28,000 students between how much they drink and their GPA. That's for the two-tailed test. We'd have to cut this in half. If we cut that in half, we get a little over 5. And if we cut this in half, we'll get exactly what the t gives us for the one-directional test. So let's go to our t. And our t had 62 degrees of freedom, n minus 2. We got the square root of 2.58. We said that was 1.606. And now we compute our p-value, and sure enough, that's half of what we got before. Right? Isn't it half of what we just got before? Well, easy way to check, let's do two tails. And then we'll get exactly what we got with the f-test. So if we didn't know, we said, hey, maybe drinking's going to affect your GPA, but we have no idea whether it's going to make it go higher, wouldn't that be amazing, or go lower. We don't know. So then, like, we're more uncertain to begin with. But we have a pretty clear idea that it would probably make it go lower, so we would want to do a left tail test. There is no left tail test, but it's symmetric, so we do the right tail test. Remember, we had a negative value, negative t. This is the same thing as if we tested the negative t down here. So, and if we do that, well, we're very close to 5%. And if we got the same slope with a bigger sample size, then it would be significant. We can't reject it. We just might not have a big enough sample size to detect the difference that really exists. So we just need more precision, maybe. So we'd have to do another. I mean, I wouldn't say, oh, you can't reject the nulls. We've got to throw that out. No. I mean, just got to do it again, and certainly with a bigger sample size, if that difference exists, then we'll detect it. All right, so that's the idea, and then you can do the same exact thing with the z and the chi-squared. Remember, the z, with a bigger sample size, the z, you can see the difference. Okay, so here, let's look at the difference here. So let's keep this in mind. I'll write it down so we can compare it to the equivalent z test, and then we'll do the chi-squared. So I'm just going to write this down. It's a p-value. This is our p-value. P is equal to, for the 0.05668. All right. 6. Something like that. All right, and this one, when we did it two tails, we got. All right, so now, how would we do? Let's go back to the document camera, and we'll do it together, and then we'll be done. All right, so let's look at this. Okay, so we did that. Right, you can't have that. Okay, so now let's use the chi-square test instead of the z. So let's go back to our exam. Remember what the z was here? Our z was that. It's the same. This part's the same. We just don't make that little adjustment. So here, let's just do. So this is our chi-squared. And it's going to be the z. So remember, our z is the square root of n times r, which is the same as, the only difference between this and the capital one in this case is this can be negative. That's the capital R is always positive, and over the square root of 1 minus r squared. All right, so if we did this, we get the square root of 64 times negative 0.2 over the square root of 1 minus negative 0.2 squared. And that's going to be, what did I get when I did that? I got $1.63 approximately. All right, so now, all right, so I say that the let's write this down. Let's write down what we're doing here. So the z squared is the same thing, yeah?
So for the chi-squared equation that you have in the notebook, it's supposed to be a square root over the n, right? Since you said that chi-squared is equal to z.
Yes, I did, so let's see that. So the chi-squared is equal to the z squared. So if I square that, I get n, this r is r squared, which I'll just write this way, over 1 minus r squared. Does that make sense? That's the z squared, right? Isn't that right? Did I leave something out? Isn't that right? I'm just squaring, if you square that, I'm just changing it to a capital R. A capital R is the absolute value of this. When it's squared, it doesn't matter. It's always going to be positive. Okay? Maybe I should do the one underneath. So the f is equal to the t squared, which is equal to n minus 2 times r squared over 1 minus r squared. Right? And so this is the f with 1 degree of freedom, and in the numerator, just 1x and n minus 2, and this t has n minus 2 degrees of freedom. Now here, z has no, you don't make any adjustments for n, and you just have, but here, so how many degrees of freedom do you have here? You have 1 degree of freedom. The chi-square is, so these two are the same for the chi-squared and the f, but the chi-square has another parameter, and the f has another parameter. This one just has one parameter. All right, and it corresponds to just p minus 1 is the same. It's the same for chi-squared. It's the same as the numerator for the f. You have the same model. You see, the chi-squared, like the z, doesn't make this tiny little adjustment for how many, your sample size. And that's why they become, when your sample size gets really big, it doesn't really matter. 2 relative to n becomes sort of insignificant. That's why you can use these with big sample sizes instead of those. All right, so now we have this, and what did we say it was? Okay, so all right, so our chi-squared would be what? It would be 64 times 0.02 squared, which is 0.0, sorry, it was 0.2 squared, right? So this over 0.96, right? This one was 62 over the same thing. And so now, this one's going to be a little bit less than that one. Here we get 2.67, and here we have 2. Was it 5.8? Wasn't it 5.8? And then the square root of that was t, and the square root of this is f. We can do it. I just want to let you out early, but it's 64 times 0.04 divided by 0.96. That's all I'm doing, and that's what I got.
and then I take the square root of that, and I'll get my z. Whoa, I did it correctly. So it's second square root of 2.666667, and we get 1.63. All right, that's good enough. Now I just want to show you the last thing, how to get these p-values. So we already got the p-values for these, and we said that we have that already. We have now I just want to get the p-values for these. Okay, and these are going to be a little bit smaller. Okay, so it should be a little bit smaller than this t-stat here. A little bit smaller than 11.3. So let's just check it out, and you're going to play around with this yourself. So we'll check it out, and let's see what it is. So if you want to go, now we're going to go to our chi-square distribution with 1 degree of freedom, and now we have 2.67, 2.67, and we want to compute our, yep, it's a little bit smaller. It's 10.23, and look what happens. When you get bigger, more degrees of freedom, look what happens. It's going to look like the normal curve. Like I'll just do 9 degrees of freedom. See, if you get like 50 degrees of freedom, or 100 degrees of freedom, so 100 degrees of freedom. You see, it's going to be like the normal curve with 100 in the middle. And now, same with the F. With more degrees of freedom, it's gonna look like a normal curve, but centered on 1. But now let's go to our normal curve, and now we're gonna say the square root of 2.67 was 1.63 something. Can't remember exactly what it was. And now we don't have any degrees of freedom. We compute and we still have, see we have about 5% in the tail. And if you have 2 tails, you're going to get exactly the same. That's exactly the same that we got with the chi-squared. So that's pretty much it. So I'm going to let you out now so you can, if you have a question on your exam, you have plenty, you can do your homework now.